So, brainstorming ideas for all these geospatial technologies and the geospatial tools that you can take advantage of and use inside and outside your classroom. We have the cartography, GeoConcept. So this is an application on how to monitor, to map, let's say, the differences between the World Mercator map projection with the actual size of the continents and the countries. So we see that the World Mercator map that we have in our schools, or that we see in printed form everywhere, is lying to us, let's say, somehow. So the actual size of Russia is way smaller than we think. The actual size of France, it's even smaller, of the United States, of Greenland, of the North Pole, Antarctica. Only the size of Africa and Latin America, and maybe, let's say, of Australia, have the actual size that those continents have as a globe. So this is one tool for primary school students. Other tools on how to take advantage of thematic mapping, and here we see the education spending in the US. So the students can start reading maps, identifying patterns, evaluating representations, or creating their own thematic maps. Something, let's say, more fun, how some people are mapping the shots that Kobe Bryant ever took. Still, this is a map at a small scale, but it's a map. So the students still may identify patterns, how many shots Kobe Bryant made, how many he missed, etc., etc. Another GeoConcept, map storytelling. Here we see how we can map the refugee crisis using GIS tools. Here we are using ArcGIS Online, and we are creating, let's say, our own stories on how people moved and traveled from their respective countries. But we also have a partner here in the GEO-Academy project working on these thematic areas, spotlight innovation. They organize every year a map competition. 2 years ago, the map competition was focusing on the refugee paths here in Greece, mapping refugee stories 100 years after the 1922 events. And last year, the map competition was focusing on mapping accessibility. Can my schoolmate in a wheelchair come to my school? And this year, the competition is focusing on water and water management. So via map storytelling, we can, let's say, explore, let's say, different thematic areas from social sciences and history and health sciences, or anything, not just earth sciences. And of course, we have GIS. These are some learning scenarios, some lesson plans we had created during the ghosting project, and we have uploaded on the GeoObserve platform on how to identify potential landing sites on the Moon and the Mars. So we are showing to teachers how to download geospatial data either for the Moon or Mars. They can create a 3D surface of Mars. We will do that today for France, actually. And then by using different criteria, different maps, the students are trying to identify the optimal site, let's say, where their mission and the rover will land either on the Moon or Mars. Some other activities related to GIS, how to create your own GPS using QGIS platform. So the students are downloading OpenStreetMap data and they start experimenting with starting and ending points, intervening to those data and modifying those data, and how they can calculate shortest or fastest paths, or how they can create, let's say, a GPS that avoids obstacles. It's not that complex, only, let's say, 3 or 4 different commands. And the students really enjoyed it. We have tested this activity with lower secondary school students. Other activities related to history, here about the ancient tunnel of Eupalinos in Samos, here in Greece, and how Eupalinos, an ancient mathematician, if I'm not mistaken, he managed to bring water to the ancient city of Samos by drilling a mountain from both sides at the same time, and the workers were met 11 years later in the middle. So to do that, Eupalinos used, let's say, geometry. And actually, he used the Pythagorean theorem. The thing is that Pythagoras was born 500 years later. So still it's a mystery how Eupalinos solved that problem, but we are solving this problem using QGIS, topographic maps with contour lines, and we are following one approach on how Eupalinos solved this super complex problem. Some platforms and of course activities related to GIS and Earth observation. We have the Map Maker. It's an online platform, of course powered by ESRI, where teachers and students may use and visualize data, create their own activities. Also, ESRI is a GIS provider. They have created lesson plans, geo-inquiries, both for primary and secondary school students, based on the Map Maker application, which are really impressive about many different thematic areas. Of course, we have the Copernicus browser. We are becoming a little bit more scientists and how we can visualize satellite images or model data worldwide about air quality, about climate change, about the marine environment, about everything. Still another platform on how to visualize the bathymetry, let's say, for example, of the Mediterranean Sea, of Baltic or North Sea, how you can visualize by pressing just 2 buttons the substrate and the geological formations in the Mediterranean, or how you can visualize habitats, marine habitats. Here is another application made from the United Nations. Pretty impressive, with time lapses and different sustainability-related variables and how they're changing from 1980 until today. Here we see global CH4 emissions from the 1980, and there is a time lapse. Of course, it's just this is just a screenshot in my screen. You don't even have to log in. You can just visit this platform and start showing to your students different types of data, but still it's a GIS platform. How we can map and monitor Earth from space. So Earth observation, one of our geo concepts. Here we see some differences in Dubai during the last 20 years. From Landsat satellite images, how was Dubai 20 years ago and how it was in 2020, the urban expansion patterns and some space-time changes. Other concepts related to natural disasters and how we can map from space volcanic eruptions. Here is the Etna volcano. 2 days, let's say, before the eruption, apologies for that, 2 days before the eruption, and 1 day after the eruption, and we see how the lava flows and how this is captured from satellites. Other activities, the Aral Sea example, and how the volume of water in Aral Sea changed from 2019 to 2025. Of course, in the Aral Sea, we had major changes from 1970 until 2019, but still we can map that. All these visualizations are based on Earth Observation Browser. Earth Observation Browser is also made for teachers with a lot of tutorials and support material and lesson plans. So quite easily your students may recreate these comparisons, let's say. Some coding activities using Python. It's not that complex. We are uploading lesson plans. For instance, this one on how students using 12 lines of code may model, let's say, the sea level rise. An exemplary case here in Greece. The students are modifying the code and they are testing different scenarios. This is an area here in Greece, in Evia and Skiros Island, and how the area will change with 5 meters and 25 meters and 50 meters sea level rise. Okay, 50 meters, it's impossible. It's a biblical disaster, but for students, it might be fun. Other activities with coding. As you probably already know, we had a lot of earthquakes actually here in Santorini last month. In Santorini, we also have one of the biggest volcanoes in the Mediterranean, and we prepared an activity for our for students on how they can download data, earthquake data, from the University of Athens Seismological Laboratory, and with a few lines of code generated using ChatGPT actually to create this visualization you see here on the top right corner with different earthquakes, their magnitude, and of course the legend, or even how to identify the epicenters of those earthquakes. Robotics and light pollution, because as we mentioned, we have this geotopic focusing on STEAM activities and robotics. This is how we map light pollution from space. And to the bottom left corner, we see an activity from students. It was a project-based activity where students developed, let's say, this route where the car is following the route, and every time the car is approaching a light bulb, the light bulb turns on, and when the car is moving away, the light bulb is turning off, in order to save, let's say, energy and reduce our energy consumption patterns at a city level, for example. So that was the first part of today's workshop. Some key takeaways: spatial, green, and digital skills matter, and they are interrelated. We are going to discuss a little bit more about that during the workshop. You may use different geoconcepts: GIS and map storytelling, GIS and cartography, map storytelling and cartography, robotics and cartography, earth observation and cartography. Feel free and do not hesitate to integrate geospatial tools and methodologies and add a geospatial dimension and component to your activities. Please join the GeoObserve community and benefit from its resources. Explore different training opportunities at national and international levels, and via those training activities and those workshops we're conducting, we truly believe that you will become a spatial thinker. One activity we created actually 4 years ago was on how to explore GIS sciences capabilities for offshore wind farm site prospecting. The core idea was to test this activity with primary school students, 6th graders, and how we can, let's say, transform this multi-criteria decision-making concept. It sounds complex, I know, to a hands-on activity for primary school students, where the students are trying to identify optimal areas here in Greece, in the Aegean Sea, and place their offshore wind turbines. This is something that we're going to test for France during our workshop later. So this is our study area here in Greece, and the core idea is that we are preparing maps of different criteria that the students are using, those maps and those criteria. They are combining those maps somehow, we will show how, and they are trying to spot a place in the Central and North Aegean Sea and say, okay, that's the perfect spot to place offshore wind turbines, and then send this energy to different islands, or in Athens or in Thessaloniki. So to do that, we have to introduce the topic first to the students for 1 hour about what offshore wind turbines are, why we use offshore wind energy, and which are the most critical aspects when we are trying to find optimal areas for offshore wind turbines. So one of the main criteria, and the most impressive one maybe for students, is the bathymetry, that we are trying to explore depths up to 200 or 500 meters and place either floating wind turbines or bottom fixed wind turbines. The second criteria, and even more important, is the wind speed. We need to identify areas that it's windy. That's what we need. So we have our study area, and we created, using QGIS actually, different maps for each one of the criteria I'm going to show. The first one is the mean wind speed. So we prepared maps, and here a map for the wind speed with color differentiations. Red or dark red areas, not the windiest ones, and light green or dark green areas, the windiest ones. So this is our map number one. Map number two, bathymetry. Red areas, we have increased depths, but still we can use floating structures. The green areas are for fixed bottom structures, and it's cheaper to place wind turbines there. The second criterion, of course, an environmental one, we have the Natura areas here in the Central and North Aegean Sea. And here, let's say we are explaining that this criterion, it's binary. Inside the red areas, we don't go. Outside the red areas, we might go there and place wind turbines. And the last three criteria, one is focusing on the distance from the onshore cable junctions, because we are explaining that our offshore wind farm needs to be connected to the onshore grid. And here we see the distances from potential onshore cable connection points. Red areas, more expensive. Green areas, less expensive. But still, we can explore some red areas. And here the distances from ports, because we have the operation and maintenance activities, installation and decommissioning. Red areas more expensive, green areas less expensive. And of course, the wind speed, or the potential energy produced. Here is the opposite. We are trying to trick them. Red areas increased energy, green areas less energy produced from our wind turbines. And the next step is that the students have to combine, they're working in groups of 2, they have to combine those maps. Before they do that, they have to go on each one of those maps and create 3 small circles at the size of a €1 coin. So they have to create 3 circles in areas that they believe, for each one of the criteria, that they are the best areas. So here on the left, we see that for the wind speed, for example, we are choosing those 3 areas inside the circles. For the bathymetry, here on the right, the same. And to do that, we are using a rice paper, of course. The same thing for the distances from the onshore junctions, cable junctions, and from ports, 3 circles on each one of those criteria. And the same thing for the environmental criteria and the energy criterion. And in the end, we are performing a multi-criteria analysis, because the students are overlaying the rice papers, and they're trying to identify the optimal site in places, in regions where we have an increased concentration of circles. And more or less, this is the way that scientists actually work using GIS and geospatial technologies. They are combining and overlaying different criteria, and they create suitability maps. So since the students have selected an optimal area, then we provide them with a list of the number of houses in different islands. So we have our offshore wind farm. It will be placed, let's say, close to Athens. And we want to send the energy produced to this island or this city. And since we have the number of houses, we may estimate the number of wind turbines. So here start some calculations that the students perform. Simple mathematics. We have the number of houses, for example, here, let's say in Athens. How many houses? 1 million houses. We see the sizes of the wind turbines. If we want to use a big turbine, we can produce energy for 8,000 houses. So they make this division and they estimate the number of houses, but a big wind turbine is quite expensive. So you may consider a smaller one, which is cheaper, and it can produce energy for, let's say, not so many houses, but it's cheaper. So they also have the costs, because they found the number of the wind turbines, and now they can estimate the total cost of the wind turbines for their offshore wind farm. And this is only the top part of the offshore wind farm. We have the bottom part. And what is the cost per wind turbine for a monopile foundation if they have selected in the bathymetry criterion to go near the shore, for example, and what is the cost for a floating foundation. These are actual costs. So they are more or less pretty close to the reality. They are also estimating using Google Earth or OpenStreetMaps the cables cost. They're using Google Maps to estimate, they have the map, the distance from the offshore wind farm to the onshore connection point. And they know that for 1 meter of cable, we have to spend 2,000 euros. So for a 50 kilometers cable, you know, the cost is quite increased. And last but not least, they are using nature-based solutions for the foundations of the wind turbines. They are trying to make their offshore wind farm to be, let's say, environmental friendly and improve or enhance, let's say, the habitats in those areas. And still, they can use some concepts per wind turbine to create some artificial reefs. So we have reef cells, tube reefs, layer cakes, but they have to pay for all of this, or to cover the cabling systems. So we are giving them a budget. And the main challenge is to create their offshore wind farm using this budget to create or produce a lot of energy. The budget is categorized based on the area that each team has selected. For floating structures, we might give them, let's say, 2 billion euros, or for bottom fixed offshore wind farms, it might be lower, like 800 million or 900 million euros. And more or less, that was the first activity. We tested this activity for 4 years, and the results were quite impressive. I mean, the students loved it. I repeat, 6th graders. It was, this activity lasted 6 hours, 6-7 hours. 1 hour for the introductory part, 1 hour in the end for the evaluation part, because an expert is collaborating with the students, is guiding them, and of course their teachers. And the actual hands-on part was 6 hours, 3 hours to identify the offshore wind farm site working with the maps, and another 2 up to 3 hours to make these cost calculations. How GIS is integrated? They used maps. They tried to read those maps and identify the optimal areas. And of course, the teacher created those maps using QGIS platform. And this is what we will try to do today for France, actually, to create some criteria, bathymetry, wind, or Natura areas, and perform, maybe, if you like the activity, of course, perform this activity with your students. I'm moving to the second activity. Feel free to interrupt me if you have any questions or if you want to add something. We want this workshop from now on to be more interactive, let's say. The second activity was focusing on nature-based solutions. Lower secondary school students, 7th to 9th grade, and the core idea was to make still a project and challenge-based activity, make the students go outside, explore their city, and protect their city using nature-based solutions. So there was an introductory part where the teacher and some scientists or experts on nature-based solution, urban planners, etc., we're discussing with the students on what nature-based solutions are, what are the major problems we are facing nowadays because of climate change in the big cities, for example, like Athens, where we don't have, let's say, any green areas or pocket parks, etc. So the students are trying to feel the problem, to understand what nature-based solutions are and why we need nature-based solutions because of climate change, temperature increases, etc. To help the students, we created some cards with superpowers about different nature-based solutions concepts. So the students first are exploring in groups of 5, of course. They are exploring those cards. They can read about different nature-based solution concepts, and they can see their superpowers. For example, here on the left, we see some forested green areas. Still, they have some cost to be installed and to be maintained for 25 or 30 years. But they have some effectiveness against flood risk. They reduce the heat island effect in the cities, and they have an environmental, let's say, added value. On the back side of the cards, we have a description. And here you can see some examples of different nature-based solutions concepts, urban gardens, forested green areas, and many, many more. We have these cards and we will share those cards with all of you. Of course, they are in English. So that's the first level. The students are learning about nature-based solutions. Okay, the second level, the second part of the activity is that after the students have identified what nature-based solutions are, how they can integrate nature-based solutions in their city. They're using maps. I'm going to show you within the next slides. They need support. They need to identify what is their prototyping idea, as we mentioned in the Living Lab methodology. So they have to create something. It might be an outdoor activity and go outside and collect data, take photos of some potential areas for nature-based solutions implementation. They can take an interview, conduct an interview with NBS, nature-based solutions experts, with community leaders, etc. And after they have finalized their prototyping ideas, they can combine different prototyping ideas. They should identify potential societal actors. We were trying to explain that your teachers or even some researchers might not be superheroes and they don't know everything. So try to find information, try to find some ideas. You might contact a soil expert, a local artist. You might discuss with your parents, because some of your parents might be architects, NBS solution experts. They might working on the agriculture sector, and they know about soils, on how to develop a community garden or a school garden, etc. So you need information. So ask your parents, ask your teachers. And in the end, if you want something more than that, you may send an email to university researchers or to companies working on nature-based solutions. So the core idea is that the students are working in 3 different phases. First, the introductory part and what nature-based solutions are. Also, during the introductory part, we are explaining what is the problem and why nature-based solutions help. So we are showing to students some graphs and some maps from temperatures here in Athens, because the case study was here in Athens, on the increasing temperatures during the last 3 summers here in Athens. We are showing and we are using GIS that we created actually about an urban heat island indicator. Here we can see in this map the vulnerable areas when a heat wave is coming. We are explaining then to students how we use maps, Earth observation, and how we are collecting data about all these analysis. The students may zoom in or zoom out on those maps, and they can identify some prone, let's say, areas. And when they identify the area they want to go and implement some activities, they are using Google Earth. They are printing the map like this that you see here. Here is a map from Cyprus. We are printing the map. We are giving the students the map, and they start integrating different nature-based solutions. Maybe on the rooftops, it might be a garden on a rooftop. Maybe it can be a pocket park. They have the cards with all the superpowers from the different concepts. They are testing different prototyping ideas. They might go outside to the field and take photos and get some interviews, or they might create a poster, but they are using those maps. And this activity lasted, let's say, for 15 hours. The introductory part was for 2 hours. We also had some experiments about nature-based solutions. The core part, working with maps, estimating the costs, and creating their prototypes, lasted for 10 hours. And at the same time, in the last 5 hours of the project, the students were trying to identify external societal actors, collect information, and improve, let's say, their prototypes, no matter what the prototype was. When we perform, let's say, geospatial analysis as GIS experts, we are using different types of data. Some of those data might be the boundaries or the administrative units of an area. Some other data might be the exclusive economic zone. Other data might focus on Natura areas or environmentally important areas like we showed in the first activity, or the bathymetry or the elevation. There are tons, or okay, not millions, but thousands of open repositories we can download those data. So for France and for today's workshop, we have downloaded administrative units from geo-boundaries. You don't have to download anything. Everything is on the Google Drive folder. If you didn't download those data, feel free to download them now. So for France, we have downloaded this file here, administrative units from 2022. It's actually the shorelines and the boundaries, the onshore boundaries of France. We also downloaded the exclusive economic zone. Here is another site, marine regions. It's super simple. We select save file here and download, and you see the exclusive economic zone of France, because we will try to recreate some maps for potential offshore wind farm sites. And last but not least, we used some data related to the wind speeds and the bathymetry for France. And this is the Global Wind Atlas. There is also the Global Solar Atlas. You may use it directly as it is. You can zoom in, zoom out, identify patterns here. Here we see the mean wind speed or the wind power density. It's still loading if we place a wind turbine. And also we can select the height above ground to see those layers visualized. Also, we can visualize topographic layers. Here is the bathymetry, or we can download data like we did here on download GIS files and API access. And you can select here for France, for example. You can select the wind speed layer. We will explain what type of data are these. The height, because the wind turbines have a height. If we select a small wind turbine, we might download data for the wind speeds up to 50 meters above sea level. For bigger wind turbines, maybe 150, or we can directly download elevation bathymetry data by pressing the button download. It's super simple. And for France, we found this repository here from the République Française, INPN, Données du Programme Natura 2000. Apologies for my French, it's been since 2005, and we can download the marine protected areas, not only the marine, the Natura areas for France, by selecting file here and download. It's super simple. Moving back to the presentation, and before we start explaining what those data are, let's have a 5-minute theoretical part. We are talking about geospatial technologies and geographic information systems and everything, but before we start our workshop, we want you to know some, let's say, categorizations about different spatial data types and how geographic information systems work. Keep in mind that when we are talking about geospatial data, we have in mind two spatial data structures. Vectorized data, points, lines, or polygons, and we are trying to represent the Earth's surface, and everything is included on the Earth's surface by using a point. And point could be, let's say, a city at a different scale, or a tree, or a human, or anything. Or as lines, a line, it could be the road network, or a river, or let's say some boundaries, etc., etc. Or we can use polygons. A polygon might be a forest, might be a lake, might be a city if we zoom in, let's say. So we have vectorized data, vector data. And when we are trying to download vector data, we have not only one, some major types of vector data are called shape files or GeoJSON files. So when you are trying to download from now on vector data, when you see the shape file option, that's perfect. The second spatial data category is raster data. It's like we call it pixel-based data, like you see here on the bottom. It's like we are having different numbers of rows and columns with different pixels, and we see the difference and how vector data are transformed to raster data. Here is an example. On the left, we see some vector point features with this X mark. On the right side, we see this grid, this raster surface, and how these points are translated into pixels. The river network, here on the left as lines, and on the right as combinations of pixels, and the polygons on the left and how they're translated as rasters. Are you using raster spatial data types in your daily routine? What do you think? That's a question. feel free to open your microphone. Do you see any raster images? What do you think? Maybe while watching TV, whatever you see on the TV screen is a raster image. That's why we have the TV resolution, 4K, everything, because we see pixels. So the image on our TV screen is a raster image, actually. The satellite images are raster images, pixel-based images. So keep in mind that we can use both vector or raster data to translate, let's say, or move what we see on the Earth's surface in a digitized world. And some basic data structures for raster files are TIFF files, as they're called, or JPEG, it's still a raster image, or GeoTIFF. But the TIFF images and the GeoTIFF images are geolocated. The JPEG image is not geolocated. We don't know the exact, let's say, coordinates of each one of the pixels on a JPEG image on the globe. And that's the problem. We only know, let's say, the coordinates on a Cartesian system. The second key, let's say, categorization is the way we are trying to explain where everything is located, either on the globe, as we see on the left image, or on a flat surface, on a two-dimensional surface. That's why we are using both geographic coordinate systems and projected coordinate systems. Geographic coordinate systems to, let's say, define where the data is located on the Earth surface, or projected coordinate systems that are telling us how to draw a flat surface like on a paper map or a computer screen. And this is linked to the fallacy of the Mercator projection that we showed before with the different sizes of the continents and the countries, because the actual sizes are on a geographic coordinate system and the Mercator ones are on a projected coordinate system. So we are using different coordinate systems like we're going to use today. And now let's start. Here we show how we downloaded the data you have on the Google Drive. And let's start diving into the QGIS platform. Let's load QGIS platform. If you open for the very first time your QGIS platform, you will see a screen like this. If someone loaded QGIS, please approve. Do you see the screen? Someone tried to open QGIS. To do that, from the Start button on your computer, you can go to all applications and scroll down, QGIS 3.40.5, and open QGIS Desktop 3.40.5. It will take some time for the very first time. And when you see the screen, you want to create actually a new project. And you see these words here, EPSG 4326, WGS 84. That's a geographic coordinate system, the global geographic coordinate system, the world geographic system, WGS. It's a geographic one, so it is using degrees. Let's create a new project. On the QGIS screen, you may see, let's say, some important toolbars and windows. We have here on the PowerPoint slide the most critical components of QGIS interface. The green one is the main toolbar. Everything you need to do is in this toolbar here to create a new project, to open a project, to save your project, or anything. You can add layers. We're going to show how. You can install more tools. You can process vectorized data, shape files, or raster data. You can use web applications. What else? Or you may make the toolbox window appear and disappear. So this toolbar is super critical. When we refer to the main toolbar, this is the one we mean. Another important feature of QGIS is the purple one window here, the layers window. We don't see anything yet because we haven't loaded any data yet. But if you go, let's say, for example, to web here, quick map services, OSM, OpenStreetMaps, we can load OpenStreetMaps. And you see here on layers, the OpenStreetMaps, it's a base map. We can zoom in, we can zoom out, we can go, let's say here in France, we can click on layers to hide OpenStreetMaps, or we can click it again. It's like we are using our Google Maps. It's more or less the same. Or you can load the data you've downloaded, shapefile vector data and raster data. Let's load some vector data for France. So to load data, you are using layer here on the main toolbar, add layer, and we want to add vector, not raster yet, vector. So we will use this button here to browse to our computer folders. I have everything saved. I created a new folder with the name Training France Data, and let's load the administrative units. You will see many different types of files here with the same name. The only file we need is the SHP file, shape file. We press this, open, and add. And that's what we see. We see the administrative units of France overlaid on top of the OpenStreetMap. We can also drag this here, and it will disappear because we are overlaying the OpenStreetMap, or do the opposite again. We can also load the exclusive economic zone vector layer. And to do that, we are following the same procedure, layer, add vector layer, and to the folder you've downloaded, it's EEZ _ France, and we will load the shapefile for the exclusive economic zone, add. And this is the exclusive economic zone for France here. And we can also load the Natura areas. The exact same process. I know it might be boring, but we will need that. We can go back, Natura areas, France, and the file, the shape file, keep in mind, we are only searching for shape files. We can also restrict here the browsing to shape files, and we will load the ZPS zones protector or zone protector or something like this. And we don't see all the Natura areas because they are below the administrative boundaries. So these are the Natura areas for France. So we have the Natura areas, the exclusive economic zone, and the administrative units. All these are vectorized data. You see, they are polygons. We can change the colors, of course. Something you can do is, let's say here on the boundaries, you can double click. I'm explaining again how we load this data. Add layer on the main toolbar, add layer, add vector layer, and you are browsing to the folder you've downloaded. And you are opening just the shape file. We can change the colors. If you double click on the geo boundaries, we can select here, it's the symbology field, simple fill color, and we will reduce the opacity. It will be transparent. and we press OK. And now we see just the outline of the administrative units in the base map. Let's show it again. Geo boundaries, double click on it, symbology on the left panel here, simple fill color, and we reduce the opacity to 0. And it's transparent. We can also do the same for the exclusive economic zone, simple fill color, opacity to 0, and OK. Or we can change the outline color. Simple fill. Let's try the stroke color, maybe it's this one, and we want a red color, and we change, you see, the boundary, the administrative units boundaries colors. Let's turn it back to black, or there are some predefined options here. For example, if we select this, it will be like a pattern, etc., etc. Since we did that, let's load some raster data. Raster data, the same procedure. Layer, add a raster layer. And we are browsing to the training France data. And here we will select the wind speed image, like you see it like this, and the elevation image, which is this one. France elevation underscore W underscore bathymetry and France underscore wind speed underscore 150 meters. And let's add them. And now everything changes. Now we don't see polygons or lines. We see some polygons because they are overlaid, but we see the wind speed first for France here and the elevation and the bathymetry. We can also change the colors, but my colleague Eleni will show you later how to change the colors. But you can read the data. On the wind speed raster surface, let's remove the other layers, the Natura areas, the boundaries, and the exclusive economic zone. You can see that we have wind speeds at 150 meters above sea level from 1 meter per second to 18.5. Still, we can change the color. I can do that, but you will do that as well later, just to enhance the visualization. You can see the wind speeds in different colors. Wind areas in red colors, non-wind areas with dark blue colors. We know that there is a part here in France on the south east coast that it's quite windy, or to the northwestern part of France. Let's overlay the boundaries on top here. Okay, here. So there are some windy areas and some less windy areas. You can also see the elevation and the bathymetry. We can double click. Still, you will do this procedure with Eleni, but to change the visualization, you can see here with red colors that we have some depths of 4,660 and 49 meters, or we have some mountainous areas, of course, the Alps, obviously, up to 3,969 meters. So what do we want to do? To create the maps for the offshore wind farm activity, we want to cleave only the offshore areas for the bathymetry here, and also for the wind here, and also for the Natura areas here, because we only want the Natura areas in the offshore, the marine areas of France. Before we start using the processing tools, keep in mind that we mentioned about geographic and projected coordinate systems. And now we are using a projected geographic coordinate system, WGS 84. So before we start our processing activities, let's go to the project. On the main toolbar here on the top, project, properties, and let's define the CRS, coordinate reference system. It's the WGS. So that's the actual visualization of France and of all of our data. But sometimes, and you may hear that on the news or from geographers or topographers, we are not working with geographic coordinates with degrees. We are working with projected coordinates. So we need to transform all of our data to a different coordinate system, a projected coordinate system. And for France, the projected coordinate system is Lambert EPSG 23 something. Let's see again. Properties here. And for France, it's the EPSG 2154. So we want to transform everything to this projected coordinate system. You don't have to do that. We did that already, and we sent you the data, because when you see the geo boundaries projected, reprojected in the folder is the projected version of the geographic dataset. Or for the ZPS, the marine protected areas, we have the ZPS reprojected. If you go to the layer, add layer, and vector layer, in the folder, you may see the ZPS reproject. You have it already. These are the reprojected files because we want to work on a projected coordinate system. You don't have to do that now. But if you want to do that, by typing on the processing toolbox here on the right, reproject, there are some options on how to use different tools for rasters to reproject it. One by one, the data sources, the elevation bathymetry, the target coordinate system. You don't have to do that now. It's the Lambert 93 from France. And keep in mind always to save your data to a new file. We did that already. You don't have to do that now. We also have detailed instructions in the PowerPoint presentation. So since we did that already, we are moving from the geographic coordinate system, EPSG 26, to the geographic, the projected one here. And since we have our projected, reprojected datasets, we can start the processing activities. So let's create first a 3D surface. It's not that difficult as you think. Let's say a 3D surface, I'm not going to show you yet, a 3D surface for the elevation and the bathymetry file. To do that, we have to install one tool, one plugin, as we call it on QGIS. And if you press here on top, you should do that because you don't have this plugin. Main toolbar, plugins, manage and install plugins. We will download our first plugin. It's called QGIS 2, the number 2, 3GS. And if you type it, the plugin will appear here. You may select it and press install. I don't press install because I have the plugin already installed on my computer. So I'm showing again, main toolbar on the top, plugins, manage and install plugins, QGIS 23GS. I can send it here on chat as well. QGIS to 3GS. You select the plugin and you install it. Using this plugin, we will try to create a 3D map visualization for France. It's not that difficult. When you install the plugin, here on Web, main toolbar, Web, QGIS to 3GS, QGIS to 3GS exporter, we will try to create an online map, and we select here the elevation bathymetry reprojected. So we select it and we will zoom in. We zoom in, we zoom in, and we will see something like this. In the beginning, it will not be like this because you have to select here on the scene settings. For you, the Z axis exaggeration will be 1, what we see in real life. And in real life, because the Earth is huge, you don't see any difference. So when you open it, it will be like this. But we will try to enhance the visualization for our students by pressing here on scene settings, and the Z exaggeration value will be up to 50. We will try to stretch everything and make it a little bit more impressive. So now you have a 3D visualization with the Alps here, with the depth values here. We see some increased depth areas. I'm not selecting any polygon because it will take some time to load those data, but with 2 buttons, we created a 3D map, and we can export this 3D map and use it to our website, for example, or to a website we may create or our students may create for a project. Export to web, QGIS to 3GS exporter, file, export to web. Here, feel free to create a new folder. I've created a new folder called 3D. Select this folder to save the results. And don't forget to activate those 2 buttons. Preserve the current viewpoint, this viewpoint, and enable the viewer to run locally, so that the viewer, the tool, will be able to read the paths on your computer. It's not stealing any data, just to load the data. And press export. And when you press export, you will get to the 3D folder you've created. My folder is on the training France data, 3D. You see this HTML file index. It's just a link you can share with the students, may share with their friends, with their parents, or they can integrate this link to their project by showing how the 3D visualization of France, exaggerated, of course, is. So with just a few buttons. So that was, let's say, the first actual use of GIS. And a second one is, as we mentioned, that we will try to clip only the offshore areas. And it's not that difficult. What we need to do that is the exclusive economic zone polygons, the wind speed data, and the elevation bathymetry data. And we want to process those data, okay? Keep in mind the processing toolbox. There is one simple button here to search and type clip, C-L-I-P, clip. We want to cut, to clip something. We want to clip the mainland of France and keep only the offshore areas. So clip, 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 clip. We may clip first for a raster here, because we have 2 raster surfaces, wind speed and elevation. Let's clip a raster by mask layer. So clip a raster using a vector is actually. And let's clip the elevation bathymetry dataset. Our mask layer will be the exclusive economic zone. You don't have to change the optional values, and we will just save, if we scroll down, our clip data to a new folder we have created. I can save it here on the training France data as bathymetry _ clip. And we select run here. I'm not going to do that. It will take 3 seconds, but I already have the clipped data set. And it's this one. This is the bathymetry for France. To convince you that it's clipped, we don't have the mainland, and we only have the offshore areas. And if we try to change the colors now, they might look even more impressive. Double click on the clipped bathymetry, single band, and OK. And now you see a map pretty similar to the map I showed you about Greece here and the Aegean Sea. So we have some areas of increased depth here, but also in the Mediterranean part here in France, if we zoom in. And this is our first criterion, how we can create it or make it a map. We will show you in the second part of the workshop. And if we follow the same steps again, processing toolbox here on the right, clip raster mask layer for the wind speed data, the exact same procedure. We have the wind speeds for France. These are the clipped wind speeds, and we can visualize the wind speeds here, double click, single band, and here are the wind speeds and the bathymetry here. So we clipped our data, the raster data, and we also want to clip the Natura areas. Pretty easy, not the raster extraction, the vector geoprocessing here, clip vector by mask layer. We double click, input layer. We want to clip the Natura areas, so the ZPS and the exclusive economic zone. We scroll down, we save the data, we run the tool, and the clipped marine areas for France are these ones. You see, there is no polygon in the mainland of France, only to the offshore areas. So now we may have 3 criteria about wind, bathymetry, and the Natura areas. We know it's not easy. QGIS and GIS platforms are quite complex. This was just, let's say, a demonstration, and now in 10 minutes, because we have a break now, Eleni will show you how to create maps, how to read maps, and how to use QGIS for those, let's say, purposes. So it's not easy, a lot of buttons, but when you have structured, let's say, guides, you will receive the presentation. We have the courses on the GeoObserve platform. You may create something really, really impressive, either by yourself or with your students.
See, this is a PDF file with a map that I've created in QGIS using data that I got from the internet in various sites, and this data got to get together into the same project in QGIS and resulted into a map that I decided what I wanted to show, how to visualize it, and then I compiled it everything into a map layout, as you can see. And I will show you how to do this same map, and not only the same map, but a better map than this. And also, this is a different kind of map. And you can see the first one is called a choropleth map. I think that you all know, you have seen such maps where the different let's just say areas on the map, or it can be countries, it can be regions, and so on. It can be any administrative units are colored with a different color value, with different intensities, let's just say, depending on the value of the phenomenon, of the special phenomenon that they represent. And here it is another map, which is a bit different. It's not choropleth, it's a proportional symbol map. This is what we call them. And it shows quantities, but in absolute values, where a choropleth map shows quantities relevant to an area and so on, percentages and something like that, which is quite different if you think about it. Now, with not further delay, I will go to QGIS. Let me just, close this, and maybe I will stop my camera from because it gets a lot of things. It consumes a lot of resources, and I'll go to QGIS. Okay, I will start a new project. Let me save this one just in case, just to have it, just in case something doesn't go well. Okay, this is a new project by default, as Lucas said, in QGIS. The coordinate system that we have is this one that you see here. It is EFSG 4326, which is the WGS 84, the World Coordinate System, that it is compatible with all GPS measurements. Our GPS receivers, either if it is something large, like a geotech station, or it is a receiver that we have on our phone, collects data for our location into with a WGS coordinate system. But in cartography, we have many different coordinate systems, because in cartography, we use what we call projections, cartographic projections that allow us to transform the 3D volume of the Earth into a 2D representation of it. And we know how to, with all the geometry that accompanies the cartographic projection, we know what the measurements can be, how the measurements can be on the map, and so on. But I'm not going into details here because this is a very complicated matter. I just want you to say, as Lucas said, that we will create a new project in QGIS, because today the majority of the audience, I believe, comes from France, and we gather data for France. We will use a coordinate system for our projects in QGIS that is relevant for France, and it's built by the Institute of Geography and Cartography, the French Institute. I believe it is the IGN or something like that. So this is a new project, and I can, I can add a layer here. As I told you, I found different spatial data. The data that I'm going to show you today, I found it on the web on different sites. Some data were already in this French coordinate system, but other data, most of the data, the majority of the data that you can find on the web is WGS 84. Therefore, I'm going to go here to my folder where I kept everything. I have made a special folder for today, and you can see here, I have found some data on land cover information, different land cover types. The one that the official European Environmental Agency uses, which is current land cover, CLC, as you can see here, the initials. And I have I have found for each region in metropolitan France land cover from for 2000, 2009, 2012. I have decided to show you only 2012 for Ile-de-France because the data was very complex and very heavy to show everything. But just to show you how you can use this kind of data only just to put them here. And okay, these data, as you can see, come with a special, let's just say, format. But the format that you are going to use is here, this SHP, which is the shapefile format, which is the official, let's just say, format file for geo data that come with information about their location. Therefore, this format file contains information about the coordinates of the spatial data that it contains. And I will have to, let me just put my glasses because I cannot see very well. Okay. I will show you this one. I believe I want to show you. Yes. No. This one. Okay. Okay. This one that I found is already comes with this coordinate system that I told you about before. This is a coordinate system that the Institute of Geographical, I don't know, the National Institute of Geographic Information in France has uses for France. And this is something that I wanted you to know, that once your original data has this information, QGIS automatically changes its default system to the system of the shapefile that already has this coordinate system. Now you will tell me I don't see anything. Okay, you are right. You don't see anything, but the current land cover, which I repeat, it's the European nomenclature for land cover in Europe, comes with a very nice package of styles that that visualize all the different land cover types. Let me find it here. It comes with the format SLD. I downloaded the folder with everything, so you don't have to do anything, just to load this format file, this file, as I did, exactly as I did. And you can see here, okay, all the different labels now apply and okay. And if I click here, all of you French, you can understand that this is the urban fabric that is dense, it's continuous, and this is urban fabric again, but a bit discontinuous, not as dense as before. And this is industrial zones and so on, road network. airports, and so on. And here is, of course, with green, the vegetation, with yellow and golden and so on is the Arab land, the land that is cultivated in different ways, with vineyards, with olive trees, and so on, pastures, etc. And of course, if you go here, you can see that we have the water courses and the lakes and so on, and also completely black is for the burnt areas and so on. And because I don't downloaded this data from a French site, this information came to me in French, as you can see. And if I open here the attribute table, okay, you can see only that the official code given by the Green Land Cover System and the European Environmental Agency is shown here, but this connects with the other the file that I loaded here, the SLD file, and so on. And also the other information that comes with this file is the extent in hectares for the area of its code on the map. Now, you don't have to do anything else. I just showed you that some things can come to you ready, all you can do, for instance, here, then you can do some GIS analysis, as Lucas said, and you can say how much of this area of Ville-de-France is covered with a continuous urban fabric, or how much of this region is coniferous forest, and so on and so on. Now, let's move into something more interesting, okay, because, okay, this is ready. You don't have anything to do. I remove this layer now. You can see that it keeps the coordinate system that I was working on. And now I add another layer because we are going to do our first map. I will start with the choropleth map, as I told you before. So we go here, layer, we add a layer, add vector layer, okay, because we have vector. And now let me go to my folder and go to the data. Okay, I have the data here. It's also here. Now I will load a shapefile which has only the polygons of the regions in France, the metropolitan regions in France, not the land that France has overseas, that we know it has, like Nouvelle Caledonia and so on. Only the why? Maybe because I moved it to another location. Sorry for this. I will try to, okay, to here, because I moved around things. I will extract here, don't worry. Okay, now I think we will be able to open it. Again, let me do the same thing. Let me find this. Why? I don't know. I have it somewhere else just in case. Just find it. Let me go to my downloads and I probably will find it there. Yesterday when I was doing Okay, no, it's not here. Oh.
Maybe it's a problem of the coordinate system.
No, I don't think it is, Lucas. But maybe I will do, okay, I will start something new. Okay, let's do this. Maybe you're right. Maybe it's a conflict of the coordinate system, but I don't think it is. Anyway, let me just do this. If it doesn't open now, I don't know what we can do. No, it's not a valid or recognized data source. I will try to open something that it is already here. Okay, now, because sorry about this, I don't know what is happening. Maybe it's because I have it open on another project. Maybe, Lucas, maybe it's this one because I already have it open and it gets confused. I don't know.
That's
But
true.
anyway,
That's true.
Maybe. But anyway, the thing is that I don't want to show you this. I want to show you just this and symbol and only a single symbol area. Apply and okay. And also, I don't want you to show the labels. I will, because this will be added later. Okay, so it's a bit cheating now because I have already reprojected the regions, as I told you, into the correct coordinate system. Anyway, I think all of you that you are from France, you recognize the French regions here. What I have already done, but I will remove it and do it again for you to see, is now I have this, which is a save file that I added and so on. And you see here that, okay, I have the name of the regions in France, okay? It comes with the source. It came from simplemaps.com, so you can find it there. And these are some things I did it myself. So I will do it again because I want you to show that some things you cannot, you have to do it yourself if you want to, create beautiful maps and so on, because the data you get from the web, they are not always complete, or they're not always in position to get visualized the way you want them to, or the way you envision, and the way you want so that they show something meaningful. The original data source that I got had only this, the ID, okay? And you can see here, it's the code that the French administration uses for this region, Nouvelle-Aquitaine, and it stopped here with the source. These three fields, as we say in the attribute table, I added myself. And the system, QGIS, calculated these things that I'm going to show you now. So I will try to make the same things again, and to follow the same procedure. Therefore, since I know that the information that I have is in polygons, as you can see, okay, if I click here, this polygon gets selected. This polygon, I believe, is Ile-de-France, it gets selected, and this is Corsica, okay, and it gets selected if I click on it. And these are polygons. Polygons by default, and as we know from the geometry and from our basic math, they have an extension, they have an area. And as you can see from the attribute table that I opened before to show you, okay, this area I have calculated. The data set that I downloaded from the internet does not have this information. It is hidden. It is hidden in the shape file, but it's not obvious to someone, okay, that does not know. Therefore, I make it obvious. How do I did that? Here, I'm in edit mode. You can see if you don't use this pencil icon, okay, now that I use it, I can do a lot of things. If I unclick it, some things here freeze, are not accessible to me. If I decided to edit, to change, that is the table, I can do it. Now, it allows me to add a new field. You can see here that I said area. Okay, I will say another area, extent, let's just say, so that it does not get confused. And because the area is not an integer, but it can have decimal numbers, okay? So I use this type. You can see here the types that are available to you here. You can add day and night if you have a time series of data. You can do text, yes, no, maybe it's a binary thing. Or long integers, short integers, and so on. Or you can say true or false by Boolean. Okay, use your logic. Now, decimal number, okay. And what I can do now is go here because, okay, this is not get automatically done. As you can see, I have to do it and I have to say how it's done. Sorry for this, but it gets mixed here. Let me just, okay. With this, open field calculator, okay. And if I go here, update existing field, which field? The one that I created, the area extent, okay. Now, because it is something simple, as I told you, this information is already hidden in this shape file that I downloaded, but it's not shown. In order to do it, it's very easy in QGIS. I just click here on the different possibilities that I have, different parameters, and just say for me to just calculate the geometry of the polygons that I have. Okay, so area here. And if I click, double click so that it goes here, and you can see, okay, that it calculates the area for every region, apply and okay. And if I go, okay, why? Because it is only, why it does these things now?
Because we have selected only the first polygon. We have to deselect.
Yes, because yes, Lucas. Okay, I will do it again. Don't worry. You are right. I was in select mode and it did these things that it shouldn't supposed to do. I will do it again. No problem about it. Okay, geometry.
No. Update
existing field. Yes. Area and apply and okay. And now we have everything here. You can see now that these numbers are a bit different than the one I did before. Okay. I will tell you why. okay, these numbers, if you take a good look here and here, they differ in the place, okay, you can see these are in square meters and these are in square kilometers. Okay, take a good look and see the difference between the two numbers here. Because, okay, because we have a large areas in France and so on, maybe we want this information to be in hectares and not in square meters. Therefore, in square kilometers, they are better. So for the next steps of this exercise, let's just say, I will keep this area, but you can see now, okay, that you can do whatever you want. And if someone asks me now from you, okay, and how can I change this second area extent that you created to match this? It's simple. You just go again back here, and where you have the geometry already and so on, you just say, oh, sorry. And now if I do it, they will change it. But I will not do it now, just to have two different, okay, options. But be careful with the measurement units. They are very, very, very important. And know, each time know which are your measurement units, okay? Because it's really important.
And
now,
also, just to add
yes.
here that if we are working with geographic coordinate systems and we are trying to calculate the area, our calculation will be in degrees and we will see some weird results that we don't want. That's why we are projecting. We are projecting all data. It's boring, we know, but it's something we have to do if we want to perform.
It's boring, but it's so useful and so significant, and people do not realize it because they have the possibility now to download everything from the web, and they don't understand that.
Exactly.
Yes. Okay, let me move on. I will close the attribute table now. And the other thing that I did, and I prepared for you, is that I downloaded some other things. Okay, from the internet, I downloaded some Excel files that do not come with geometric information or special information. They come from census data. They are census data, and they just, include information like, okay, in Corsica, we have this number of inhabitants. The population is so much, and so on. Let me just open this just to show you. Okay, this is the original Excel file that I downloaded from the internet from some organization, statistics organization repository. I don't remember exactly. And here you can see, okay, the different metropolitan France regions. We only have for France metropolitan. We don't have from the overseas territories, at least from this source of information. And we have population for 1990, 1999, January 1st of 2008, and a provisional population number for each region for 2025. This is this year, the current year. Okay, and you can see the different Of course, Ile-de-France has the highest number of inhabitants in France, as we all know, because Paris is there. Okay, now if I try to upload to insert this Excel file into QGIS, I will get some bad results. It won't happen. Therefore, what I did, and I will show you what I did, is I edited these Excel files, okay? And what I did is I removed all other information and I only kept table information. For instance, I removed the headings and I added here a name, a heading for this column. Otherwise, the system could not understand what I was trying to incorporate into QGIS. And also you can see that I changed here, it's Comte, and I did Comte. I changed all the letters that had an accent, the accent circumflex and so on, because the system could not understand them. Because my QGIS in English and so on, it could not understand all the French special characters. And also, to tell you the truth, is because my attribute table into which I want to connect the information on the Excel file doesn't have these special characters, as you can see. So in order for this column to be compatible with the other column on the Excel file, I had to change. And also I added some hyphens because because the original file did not have them. If I open the two, you will see the difference. Okay, you see here the accent circumflex in Ron, and you can see that Nouvelle Aquitaine does not have a hyphen between the two words, but in the CSV file that I edited, this is now contained, and the accent circumflex is gone from Côte d'Azur, for instance, because I want to match this information with the information that I have here. Therefore, this is what I always say to my students, and I'm telling you now, be aware of your data. Look at the data very carefully before you do anything else. Okay, now because I saved this in CSV, not in XLS format, so that it is comma delimited. This is what is comma separated. This is what CSV mean. And if I go now and add layer here, and you can see it allows me, the system allows me to add a delimited text layer. I'm going to find it. This is it. And if you move a bit here down to see how this is entered, to see that everything is in place, nothing is, wrong, be careful to put this here, semicolon. If I don't use this, the columns will not be inserted as they should be. The decimal separator is comma, if we had commas here, but we don't because we have, people, so we don't have decimal number, we have integers. But anyway, this is the default, and use it if you have commas and so on. And if we say add and close, now I am ready to open my attribute table here. What I forgot to tell you is that in the CSV file that I created, I added also this field. Remember that the original Excel file did not have these chains. I put it because I wanted to see if I wanted to visualize the change that I have in population for France in the 90s, let's just say. So I did it, and what I did is easy in Excel to do it. You just have to subtract the value for 1990 from the value of the 1999 year, so that you have the change within these 10 years, this decade. Okay, this is something that you can do. You can also, the same way as we did in the previous example, we can now make another field here, but I'm not going to do it, just not to lose time. So here we have our polygons. The polygons have now in the attribute table the information about their extent in square kilometers or in square meters, as I did before. And we have also this CSV file that it came to us somehow, and we pre-process it in order to be able to use it. Now, what I'm going to do is to join the two. I go here on my special, let's just say, layer, and I right-click it, and I go to Properties, and here you can see everything that I can do with it. And I select Join in order to join the two. And once I click to create the new join, okay, the add vector join, the system understands because I don't have anything else. I have this layer and, okay, and you say, and it is by default chosen, and it says to me, which field do you want to join? I want to join this metropolitan France region, the heading that I put in the column, as you remember. With which field, which field do you connect with that? Of course, the name. These are the two compatible. I have the metropolitan France / region name into my CSV file, and I have the field with the heading, the column with the heading name into my special data file. Therefore, I make this join. And it says to me, do you want to join everything? Okay, because if I don't click in any of these and I just say, just join the 90 population, I can do it, but I will leave it at that. I will have everything joined. Okay. Apply and okay. And now you have opened my attribute table. You can see that all information included in the CSV file is now included in my shape file, which contains the geometry of my regions, of the French regions. And now I can do things with it. I can do many things with it, and I can start visualizing everything that I want. Remember that I showed you a map, okay, that showed population density in 1999. Okay, because I want to do a choropleth map, as I told you, choropleth maps are all over the place, but not all choropleth maps that you see on the web are correct. In order to make a choropleth map, you need a value of a phenomenon, of a special phenomenon, like population, but you need it in some special unit. You need, for instance, population density. You need number of inhabitants per square kilometer. You don't visualize with a choropleth map just the number of inhabitants. This is wrong. This is fundamentally wrong in cartography, okay? But people do not realize it. In order, therefore, to visualize, to make my choropleth map, I have to create another field. This field I created because I did the join before and so on. And how did I do the population density for 1999? Sorry, what I did is I divided the population in 1999 with the area of its region and created this new field population density. Therefore, in order to show you how to do it, I will create a population density for 1990. Okay, pop density 90. This is a decimal number, of course. Okay. And now, if I say update existing field, here it is. Now, because we don't have the geometry, we want to calculate things from the other fields and the other values in the table. Therefore, I do not go to geometry, I go here. And what to do is, sorry, I have to just move this along to better see. Doesn't want to cooperate anyway, but I want to see something here. Okay, I want to have, therefore, the area, the population in 90, okay, in 1990, divided by the area, and you can see here, it starts calculating everything. You see, Corsica has only 28 inhabitants per square kilometer, while Ile-de-France, you see how many we have here, okay? So what I did a simple division. I divided the overall population of 1990 with the area, and I chose the area, the correct area, because also the other is correct, but it's better if we have the persons, the inhabitants, divided by square kilometer, okay? Apply, and okay. If I go here and see that it is done here. And I will perform now my visualization of the map for this, for this field. I go again into properties and I go to symbology, and instead of single symbol, which is the default, I now go to graduated symbol, because as I said, choropleth maps use these kind of symbols. They differentiate the regions, the other administrative units and so on, by color value, the intensity of the color. I choose a color RAM. For instance, maybe reds, or maybe I will do reds. Okay. And the most important thing in every choropleth map visualization is this thing here, how to classify your data. And QGIS, as all GIS systems, platforms, allow you to play, let's just say, in quotes, to see what happens when you select the different options that it has. One of the most prominent selection that we can make, and it's one of the most, let's just say, used in cartography worldwide, is this thing here, natural breaks GENCS. And here we can decide how many classes our visualization will have. And the number of classes is how many color intensity, color values we are going to utilize in order to visualize our data. I will do a first. Okay, what I did, sorry, because yes, sorry, because we have to say here the population density. Okay, answer legs. So you decide which value to happens. Doesn't want to cooperate. I don't know what happens, but it doesn't want to cooperate. Maybe because I'm in edit mode. Yes, maybe it's this one. Let me just see what happens now. Population density symbol, yes. Classify. Yes, now we did it. And you can see here that it has created a class for only 29 inhabitants per square kilometer, which is in Corsica, because this is the lowest value that we have, and created a class that ranges between 180 inhabitants and 880 inhabitants, which is Ile-de-France. If I click on apply, you can see our map here. And you can see how Ile-de-France, the region of Paris that is the most populated. Now, as I told you, you can play with this and you can decide, okay, natural breaks, I don't like. I will prefer this one. The quantiles. The quantiles, this method has, let's just say, the advantage to create groups in our data, these classes in our data, that have the same number of regions, let's just say, assigned to them. But if I do that and leave the classes number at 5 and do not change because I want you to be able to see, here what happens. The previous, let's just say, option stretched a lot the Ile-de-France. It popped out. It was the most dark region on the map. Now, Ile-de-France comes along with, I believe this is how or something, the northern part, and this one, which are very different, as you can see here. The range is very, very large, and their population does not deserve to be in the same, let's just say, color value. So I would prefer to keep the GENCS. Let me just do it again. And so, and see how this is done.